without further ado, I want to announce our speaker for today. This is GRR, Collect All the Badness, Collect All the Things, by Greg Caste.
Hi. How's my mic? People hear me? Okay. So thanks for coming. I thought I might start by asking for a show of hands. So before you walked into this room, who knew what GRR was, what it does? Well, that's awesome, actually. Who's used GRR before? Okay, there's at least one GRR developer in this room, so that's still pretty good. Just a little quick bit about me. So I'm one of the GRR developers. I sit in the Google Incident Response team in Mountain View. I also have an active interest in OS X security. I was the OS X security guy at Google for a while, so looking after the security of all our Macs. And before that, I was doing a bunch of pen testing. I led a pen testing team, mostly Windows pen testing. Did some incident response, security audits, most other security jobs you can imagine. So I wanted to start, before I kind of explain what GRR is, what that acronym actually stands for, I wanted to start where GRR started, which was talking about live forensics. And I think this really is not an optional thing anymore. I think if you want to defend your network effectively, I think you need to have some capability like this. It doesn't have to be this one, but I think that being able to respond to the many and different kind of various ways you can be compromised and the many and different environments that we have in our organizations today, it's not really an optional thing anymore. So I'm going to go through a couple of use cases to kind of illustrate this. So here's Joe's machine. It's beaconing to somewhere that looks pretty bad. So it's making these HTTP requests that are probably malware command and control. So okay, we want to do something about this. So maybe we can walk over to the next cube and grab Joe's machine and take a memory dump and do some dead disk forensics. But unfortunately, that's not going to work because Joe's here right now. He's having a really nice time off the Nepali coast in the Hawaiian Islands, and he may not be great at security, but he's actually really great at vacations. So we can't just walk over to the next cube and pick up his machine and do what we would normally do. So if we have some sort of capability like GRR where an agent's already installed and it can talk over the internet, then as long as he's got internet access, so he's got 3G on his boat there, then we can do some sort of initial triage of his machine, figure out what's going on, maybe grab copies of malware and respond to this threat. And if we don't do that, basically the options are either the data comes to us or we go to the data. So in this case, it would be awesome to go to Hawaii. That would be great. But it's probably not going to scale very well, depending on how many incident responders you have. And shipping the machine back is perhaps the other option, but it's also completely unreliable. It might be okay from Hawaii, but consider all the different countries that an organization might operate in with less reliable shipping. Maybe the disk turns up, maybe it doesn't. So it'd be great to have an agent there. So another kind of use case I'm going to use to talk about GRR today is that there's this new APT report out. Whether it's advanced, persistent, or even a threat might be kind of debatable, but there's this new report, and whether the contents of the report are amazing, what's pretty much guaranteed to be amazing is code names and logos. So for the purpose of this report, I have Bear Eagle Shark Laser, which is my APT report code name. So there's this new malware report, Bear Eagle Shark Laser, and we need to check all the things in our whole organization. So this is actually pretty complicated. So this report has, like over 50 indicators of compromise. It works on 2 different operating systems, and we've got a big organization with tons of different things that need to check. So doing this without some sort of agent like GRR is a really tough proposition. So maybe you can make some sort of management tools. You can kind of with a fair bit of development work, perhaps you can make them do the things that you want to do in this sort of scenario, but really having a custom designed tool that's ready to take on a task like this is, I think, really important. So what is this tool? So GRR stands for GRR Rapid Response. It's a recursive acronym in the best traditions of GNU, Wine, YAML, YOLO. Actually, YOLO's not. I'm just seeing if people are awake. It's not actually a recursive acronym. It works on Windows, Mac, and Linux. It works at scale. We run it at scale. It gives you access to the raw disk and raw memory of machines. It's a stable client and a stable server. We run this on a lot of machines. And we also do a lot of work to make sure that we're not eating too many system resources. So we measure how much CPU, how much memory, how much network we're consuming, and we have limits for each of those things. There's a two-party authorization system. So to take any action on a machine, you can set it up so that it requires approval from someone else. And we can hunt across large numbers of machines. So take some action across the entire fleet, so like the bear, eagle, shark, laser kind of thing. We can go looking across large numbers of machines. And this is basically the only GRR overview bit I'm going to do. So I'm talking all about new GRR stuff today. So if you're looking for kind of a general introduction to the tool, you're probably not going to get enough information in this talk. So I'm mainly covering artifacts and getting data in and out of GRR and a few other things. So if you're looking for a really general overview, definitely check out the code.google site, which I've got a link to at the end. And there's a bunch of papers and presentations there that you can look at. It's been open source since 2011, so it's been around for a while. So just back briefly to Joe's machine that's beaconing out. So in a traditional kind of forensics response to this, you might say want to build a big timeline. So you take like a dead disk and then look at the times at where these beacons were made and build a timeline around what happened during those times on the machine. So what files changed, what was written to the registry, this kind of stuff. But when we're doing this remotely, we don't have the luxury of dragging back huge amounts of data from this machine, especially over a kind of shitty 3G internet connection. So we want to do something much more targeted. So it will be that timeline analysis would probably lead us to places like, I don't know, run keys on Windows or launch agents and launch daemons on OS X, like common persistence mechanisms, or we might want to look at listing processes or listening network connections. So forensics people will probably realize that I'm talking about forensics artifacts at this point. So all these little bits of information you can imagine kind of digging through the dirt of this machine as an archaeologist and finding this priceless pottery that is the artifact that tells you how this machine was compromised or how the malware is doing its persistence. So SANS will tell you a forensic artifact is a combination of description, location, and interpretation. I think I prefer that stuff I want. And I don't expect you to read this kind of giant wall of text here. I just want to give a sense of scale about kind of how complicated this is getting in modern operating systems. So this is major browsers on 3 operating systems. How many paths would you have to know where the browser history is for each of those browsers? So there's this list here abstracting away a bunch of complexity about kind of different users and different profiles for different users. But let's say 30 paths or so for the major browsers, 3 operating systems. Just the history. So then if you think, well, okay, now I'm also interested in the cache location, so maybe when a user browsed to something, something interesting got downloaded into the cache, and I'm interested in that file, I might want to go looking in there as part of an investigation. Now you're talking about 67 paths, and you can see as we expand the amount of software that we consider, there's tons and tons of information here, and more than we can really hold in our heads properly. But I think that's kind of still what we think that we do. So as investigators, I think that we think we have this perfect recall that we can lay our hands on the exact path that we need for the IE browser history on this particular version of Windows. But it's not really true anymore, I don't think. And increasingly, as investigators operate outside of their comfort zones on different operating systems, this is more and more true. So this is what we think we do, but I think what actually happens is more like this. And the quality of information you get from a search like that really varies. So there's some great stuff out there that's peer-reviewed, that some of the best investigators in the industry are contributing to. So stuff like Forensics Wiki, maybe ForensicArtifacts.com, all the way down to kind of your just random Joe on on a web forum, saying, here's where the IE browser history is. And he's probably not going to tell you all the complexity about, oh, it's different versions of Windows, different places, different versions of IE, different places. And all of this information is kind of blogs and wikis and spreadsheets, and it's certainly not easily machine readable. So if I want to kind of consume this information and then use it in some sort of large-scale way, I can't do it at the moment. So the problems we have here are of brain storage capacity. We just can't hold this stuff in our heads anymore, and the ways we're running it down are just really bad. And they don't encourage sharing, and it means that data gets stale really easily, and there's basically like very little collaboration. People carry around text files on USB keys and contribute stuff like this to their internal wikis, and none of it kind of ever leaves their own little sphere. So these are problems. So this is what we wanted. And we built it. And it's open source. But before I'm going to talk about that in more detail, is this sounding a little familiar? Didn't we do this already? Haven't we been doing forensics for ages? Haven't we written down a big list of stuff somewhere? Isn't there like maybe a big pile of XML or something that describes this? There's certainly standards, and there's a lot of standards. But as Jay-Z says, like the kind of problem we have here as an industry is not a lack of standards. So a lot of those are actually IOC standards, so I wanted to call out. So it turns out none of those actually kind of describe this problem that I've been talking about, the forensic artifact problem. So a lot of those are IOC standards, and I wanted to call out kind of IOC versus artifacts. So IOC is kind of along the lines of, if file name this and has this string and signed by this cert, then it's bad. So there's a data description component that's like this file name, and there's also a logic component. So if this thing and this other thing or this thing, then bad. Whereas an artifact is more just like, here's where the event log is on the system. So it's mainly data description. So why haven't we done this already? Why isn't there kind of a really big kind of central repository of these things that we can all collaborate with and use that's machine readable? And I think the problem is one of kind of partly language of describing this data. So these are artifacts that I pulled from various places in the wild. It may be a little hard to read, but there's a problem with all of these. I don't know, can people see what? Anyone want to yell out what they think the problem with this data description is? User? Yeah, totally. So the problem is actually all of these things. So all of these things are specific to the machine itself. So whether the disk is on C colon or D colon or whatever colon on Windows, what users are on that particular machine, what user SIDs are in the registry. On OS X and Linux, where are the home directories, which users are on the machine. So all of this stuff, a lot of the artifacts we want to describe are in user home directories, and it's really hard to describe them without talking about which users are on the machine. And if you want to apply this to an entire fleet of machines, then you can't just put in here the number of users, every user that you need. So it's basically a problem of interpolation. So we came up with a solution for this that's a common language that we call the knowledge base, and we populate it for every machine. So it's a bunch of information about where user information. It's a bunch of information about the machine. So everything from kind of environment variables, what users are on the machine, where the home directories are, all this kind of stuff gets built by GRR, and later on we can then fill it in. So when we collect one of these artifacts using GRR, we can basically populate all this information. So we don't have to know it beforehand, and it gives us a nice way to describe where all this stuff lives. So here's an example of what an artifact actually looks like as we created it. So a couple of things we didn't want to do was write XML, and we also didn't want to create a domain-specific language. So we chose YAML, which is well supported with all major programming languages, and is machine readable and human readable. So you can see here, this is a simple artifact that describes event logs, and there's some metadata about kind of what it is, some documentation, And then the file description tells you, exactly where this thing is using the interpolation scheme I just talked about. And we also have the ability to constrain it, so this only applies to newer versions of Windows, and this only applies to Windows in particular, and a link to more information. So that's a basic kind of example of what an artifact looks like as we created them. So we have like about 130 of these. We also have about 30 parsers, so you can, there's a data description component, and then you can apply a parser to, so you can use GRR to retrieve that file or registry key or whatever it happens to be. And then you can apply a parser to it to get something more useful. These are sitting in the GRR code repository at the moment, but we're shortly going to split that out. But please take a look at these, spot inaccuracies, file bugs against us, send us pull requests for new artifacts. All of that would be really amazing. And I just wanted to show quickly, it's kind of hard to visualize just a file path, so I have this kind of collection of dots here. That's a really simple visualization I built. So blue dots are Windows, so you can see that and all the singletons and the edges, so the links between the graph are dependencies. So you can see the blue dots are Windows, and they're the most complex kind of artifacts that we have with the most dependencies. They're most interconnected, and you can see kind of here in the middle, these are the browser-based. Oh, that's Java cache files, but most of those are browsers in there. So they're the most complicated in terms of like the number of dependencies that they have. But you can see like lots of artifacts don't require any dependencies, but some you'll need to know. These are a bunch of registry artifacts over here that all depend on current control set. So yeah, I just wanted to kind of give you like a visualization that wasn't just a code path with a bunch of YAML in it. And now it's demo time. So that's enough talking. So I'm somewhat crazily, perhaps, going to attempt let me just try and make this hopefully readable for you and somewhat still usable for me. So this is a live demo. I have a server that it says localhost here, but I'm just tunneling out. So I have 3 clients, a mix of kind of GCE and AWS clients talking to a server. I have a whole fleet of 3 machines for the purpose of this demo. If I click on one of these, so you can see this is a Red Hat box. You get a whole bunch of client information here. So I'm going to start by actually collecting a bunch of artifacts from the Windows server, which is this one. So in GRR, the kind of high-level unit of work of like collect a file or look at a registry key or something like that is called a flow. So I'm going to start a new flow that's the artifact collector, and I'm going to kill a whole bunch of GUI bits here to make this hopefully readable. And here's our big list of artifacts that we have to choose from. So if I click on some of these, there's maybe a little smaller. There's a description that's appearing over the side here that is basically a HTML representation of the YAML. So this is a basic shopping cart interface. So I've got a few artifacts that I'm kind of going to collect. So I'm going to collect Windows services from the registry, the contents of the recycle bin. I'm going to do a process listing and a netstat. And I'm just going to split, so there's a bunch of options here that are kind of not really important, but I'm just going to split this out so it's a bit easier to view. So if I click launch, it gives me a kind of summary of what I've done there. Now if I get some of the GUI back and go to manage launch flows, so you can see there's a flow running here now. The little clock symbol here means that it's running. So if I just kind of keep hitting refresh on this a few times, this works. It should complete and turn into a tick like that. So excuse the kind of like small gooiness here. So I've got a link into GRR's virtual file system. So this is where we kind of put analysis results, but we can also do stuff like browse the remote file system of the machine we're talking to. So I'll demo that in just a bit, but here's the results from the artifacts I just collected. So there's a giant collection with all the 480 things I just collected, but I've split them out so you can kind of see them more individually. So this is list processes, stuff that you would expect, like PID, parent PID, who is running as, the network connections it has, et cetera, et cetera. So there's a whole bunch of those. And this is the netstat. So IPs, ports, connection state, as you would expect. Actually, I'm going to do that one last. So this is the running Windows services as seen in the registry. And this is the contents of the recycle bin. So I deleted a couple of files here so we'd actually have some stuff to see. So there's a bunch of metadata, so stuff that you would expect to get from a file system stat, so sizes and MAC times, that kind of stuff. So if I click on this, it takes me into the file system view of the remote machine. So this is file system, operating system. So that means that we're using the operating system APIs to inspect the file system. We can also use the sleuthkit here, TSK, which is to operate on the raw disk. So we can see the OS view and we can go under the OS and see the raw disk view as interpreted by sleuthkit. So this is, close from this. This is a deleted file that I retrieved from the recycle bin. You can see the contents of it here as just a kind of dummy file that I created. So the next thing I'm going to demo is uploading an artifact and then hunting for it immediately across all the machines. So this is useful in investigations where you can imagine that you've got a group of machines that maybe you think are owned, and you've got a list of stuff that you want to collect from those machines. So like collect all the stuff that I normally collect when I think a machine is owned. So it might be things like event logs and registry hives and run keys and all this kind of stuff. So I've got kind of an example of an artifact that I've just defined in YAML here. As a demo. So this artifact is actually both a meta artifact, so it collects other artifacts, and I'm collecting, in this case, event logs just from Windows. And then I'm also collecting any file that's in the user's home directory, downloads directory, that starts with the word keygen. And I'm doing that on Linux and Windows. And this is kind of to demonstrate the power of the interpolation scheme, that I can address the downloads directory across multiple operating systems, across every user on the machine, just with this simple specification. So I can upload, where am I? Oh, I think it might just be off the screen. There it is. Is it still somewhat readable? Yeah. So I'm uploading that YAML file to the artifact store now. And this is kind of the HTML view of the same thing. And then I can go into the hunt manager. So remember, a hunt is something that runs across every machine or a large group of machines or some group of machines and does something. So I'm going to create a new hunt. And this is also, actually, I'll talk about that in a sec. Let's do this first. So this uses the same interface that we saw previously, except now we have this Black Hat Investigations artifact here. So I'll give this hunt a name. This is only going to be useful for a couple of minutes. My button is just slightly off the screen here. So I can also add a output plugin. So the one listed here is write CSV file to AFF4, which means in kind of GRR speak that it's going to write a CSV file to somewhere where you can later download it with all the results. So I'm going to turn that on, and I'm also going to turn on file hashes, get them exported as well. Often we want to restrict things by operating system. Oh god, I got to get this just on the screen so I can click this. Sorry. Resolution is not doing me any favors here. Oh yeah, I could do that. Okay, seeing as I can't hit the X that's just off the screen there, I'm just going to do a little dirty workaround here. And hopefully that works. Oh, come on. Yeah. What's that? Oh, right, yeah. Yes, thank you. Okay. All right, let's try this again. I'll bump this a bit. I think I'm just going to have to start this hunt again, sorry. So yeah, I'm actually going to ditch this rule because I don't need it. Okay. And so at this point, if I was running the authorization model that I talked about, I would have had to, when I click play there to start the hunt, I would have had to get an approval from someone else before I could actually start it. So this hunt is now running. So you can see here it says outstanding 3, so there's 3 machines that have picked up this hunt, which is my entire fleet. 2 of them have finished. Now they're all finished. So if I look at results, so you can see this is the Red Hat box. There was a keygen.zip there. This is the Ubuntu machine. There was a keygen file there. This is the event log that I downloaded. And this is the keygen.exe that was on the Windows machine. There's actually a cron job that runs that generates the CSV output. So I'm just going to force that to run now to make this go. It runs every 5 minutes, but it's just too slow for demo purposes. And so now I have the CSV file here, which I can download. And this is probably pretty unreadable, but believe me that there's a CSV file here that has the file path that we downloaded stuff from, and the hashes and MAC times and file sizes and all that sort of stuff that you would want. Okay. So that demo worked. That's great. I must have made the right sacrifices to the demo gods. But in case I've given you the impression that like everything is rosy and amazing, this actually, is actually pretty complicated. So testing is quite a challenge as the artifacts grow. We just can't install every piece of software that we're trying to write an artifact for on a machine and then run every artifact. It just doesn't work very well. So ideally, I think this is where kind of a community can step in, and we definitely have a vested interest in the artifacts that we use all the time. So we use these actively in our investigations. So we want them to be up to date. We want them to work when we need them. But if there's another artifact that we don't use that often that's important to someone else, I really think that it'd be great if the community can kind of basically keep these up to date together. It would be really nice. Populating the knowledge base is actually pretty tricky. So you can imagine figuring out users in environments where you use things like LDAP for Linux machines and network home directories. What is a user in that case? Like, what's the user's home directory in that case? And you need to be careful about kind of hitting network shares that might be really slow as well too if you're trying to collect things. Also, do you include users like system on Windows or root on Linux? So yeah, there's a lot of complexity there, and fulfilling the dependencies is actually quite tricky too. So we might have 3 or 4 different ways to get the list of users from Linux. So what if one of those fails? Is that okay? Should we keep going and just use what we've got, or is it not good enough? So there's kind of implementing this has actually been like reasonably tricky. So, just stepping back to the Eagle Shark laser for a second. So we want to check all the things. So this is typically what we have to work with. It's the industry standard machine readable format of choice, which is PDF. It has a bunch of DLLs in it, a bunch of hashes, maybe some registry keys. All of these indicators, especially the hashes, are really pretty fragile. So, you think about a hash, a malware hash. Often people ask me, can GRR just tell me if this hash is on a machine? So hashing is actually kind of really bad for detection. I mean, a 1-bit difference is all it takes, right? And so maybe the malware that we get that is actually the same malware just has a different campaign identifier in it, or maybe it had a different compile time, or maybe it's a slightly newer or a slightly older version. There's a million different reasons why the hash is probably not going to match across malware campaigns, right? And same thing with lots of the other indicators here. So the file system names, they might be derived from other files that are actually on the file system. So they might be per machine specific. They might be per campaign specific. They could just be random. And same with the registry keys. So given that all of this is pretty fragile, is there kind of like a better way that we could hunt for for malware like this? What would we collect? So we saw that it wrote into System32. So we know this thing writes executables and DLLs into System32. So let's just collect all of System32, all the executables and DLLs in there. So the advantages are that we leak a lot less intel. So every time we tell GRR to go collect a very specific file path or a registry key or whatever, then if that machine is compromised, we potentially leak that information to the attacker. So now that maybe they know we're after them. So if we can just collect a whole bunch of stuff fairly regularly, then there's much less intelligence exposed. And if we do all the analysis on the server side, we might. If you did this, you might collect a whole bunch of unknown bad. So you might, 6 months from now, you might realize that this particular DLL we collected was actually part of a new malware toolkit that we didn't know about at the time. And as long as you keep that file around, then you'll have this history and another time to look at to go find maybe patient 0 on your network. And the obvious downside is, there's a ton of files. So is this actually really practical? So could you do this? In my fairly vanilla Windows development machine, this was like 3 gigs worth of files in System32. So it is practical to collect large numbers of files with GRR and to do it across, at scale, do it across a lot of machines. And I'm going to explain how that works and kind of why it's effective. So the first thing to note is that we hash files, and we never retrieve the same hash, obviously. So if it's identical on the machine, it's identical to what we've got in the repository, so we can hash on the machine and then not retrieve it. So you can see here these kind of malware-inspired file names on these two different machines. The purple file there is a bit for bit identical across the two machines. But we also we chunk files up into blocks, and so we also hash each individual block. So if we've already got this block of bits on the server, then we don't need to retrieve that either. So you can see here there's 3 files across 2 machines that share the yellow block, and there's 2 files that share the blue block. But basically, you get the idea that we only send what we don't have. And so in the GRR database, files look like just a kind of big array of pointers to all the bits of data that we've retrieved. And we only store each one of those blocks once. So practically, like if you do a big collection like this, you can use the client limits to make it work. So what we do is we use this client limit here, which says for the hunt, only run on X number of machines. So we might run it on 10 machines, say, for something that's really intensive, and we'll precede that database with like 80% of the common files. So all the files that are common across System32, most versions of Windows will probably get. And so then we can run it on 100 machines, and then 500 machines, and then we can run it on the entire fleet. And by the time we've run it on the entire fleet, we're only collecting a diff of every block that we don't have already. And you can also use the client rate limit here to make sure you don't kill your server at the same time. So this is kind of like steps up, like how many clients are running this particular file collection at any time. So I'm going to talk about input and output from GRR and kind of connecting it up to the rest of your security apparatus. I think that's an important way of using GRR and an important way to leverage the capability. And I'm going to defy convention and talk about output first, because we've collected a bunch of data now. So we've got a bunch of data in the GRR data store. What can we do with it? Can we get it out into other systems to look at it? So one thing you can do is you can register for new file events. So whether an analyst is browsing the VFS of a particular machine and downloading interesting files, or you're doing a large-scale kind of hunt collection, you can register for a new file event and then do something with it. So you can imagine maybe collecting a whole bunch of executables and then submitting them to VirusTotal, say, or something like that. You can also, as I showed in the demo, you can get a CSV output, so then you can ingest that into a database or stick it in a spreadsheet or do whatever you want to do and do some further analysis on that data. And that can be file names, hashes, registry keys, all that kind of stuff. And kind of the third way to it's probably more useful for one-off analysis is if you need to do something that the GUI is not going to cover, there's an IPython interactive console for GRR that you can use, and so you can do anything that GRR can do in there. But you can definitely iterate over result collections and analyze data in there. So okay, that's collecting with GRR and then sending the data out and doing something with it. So what about input? So you can imagine connecting GRR up to other bits of your security apparatus. So in this case, the kind of example I'm using is maybe you write this snort watcher cron job that just looks at snort logs and looks for new alerts. So you get this new alert that says, this IP to this IP, something bad. And so you figure out this IP is poor old Joe's machine again, actually. And you want to collect the snort host context artifact from his machine. So you can automatically fire off. So maybe you have an artifact that's, list all the running processes, look at listening network connections, tell me the patch level of this machine, show me the installed software, this kind of stuff. You can send that out to the client. It'll report back. And then you can imagine taking that data and sending it into your security event manager. So the thing that the analyst is going to look at that snort event in, you can send all that contextual information from GRR to that SEM. So then, by the time that the analyst actually gets around to analyzing this thing, they've got a list of the running processes and the network connections and what the machine patch level's like, already there, all ready to go. So stuff that's coming up, there's a lot more work on artifacts still, so want to split it out into its own repository so it's not in the Go repository anymore. Probably make a web interface to make submitting and browsing the repository a bit easier. Also, improving the Go use of artifacts. So when you're collecting lots and lots of artifacts at the moment, the performance is okay, but we think it could be faster. So we're doing some work there. Also, debugging them can be a little tricky. I kind of touched on this. So, if you have this kind of long dependency of artifacts that all collect things and have fairly complicated dependencies, if something goes wrong in there, it's a little bit hard to figure out what exactly went wrong and why it went wrong. So we're doing some work to make that easier. We're also looking at some of the other open source projects that our team works on. So one in particular, Log the Timeline, or Plazo is a newer version. They're also looking at using the Go artifacts. Basically, we don't want every forensics tool in the world to have to describe where the Windows run keys are, right? This is a problem that, we should be able to describe this thing once, and then everyone use that definition. So at least with the projects that we have some influence over, we're going to try and share these artifacts and use them in other tools. There's a lot of work going on the recall memory forensics framework at the moment. That's a really mouthful. Lots of development in there, and we have a Go integration that's pretty new that's going to, I think, vastly improve our memory forensics capabilities with Go too. That's a pretty exciting project. We've done a lot of work in the last few months on open source database performance. So we don't use the open source data store at Google. We use our own one. So this has kind of traditionally been a bit of a problem for people running the open source version. So we've done a bunch of performance testing. We've written new data store layers, and all that work's coming out in open source pretty soon. And should actually help a lot with open source database performance. And swapping in and out Go data stores is actually really easy. It's just a config change. So the data store itself is very abstracted away. So we've also been working on load indicators a bit. So sometimes what happens is you'll kind of run a flow on a machine and it doesn't work, and you're not really sure why. So sometimes it's the client is really loaded, so you've sent it a bunch of jobs and it's still processing the other jobs that you sent it, and it hasn't got around to doing the new one that you sent it. Or maybe the server is really loaded, like it's ingesting heaps and heaps of messages from the fleet, and it's not getting around to queuing everything, and it was kind of hard to know what was actually going on. So we've added a bunch of graphs and kind of indicators so you can have some sort of visual way to debug, kind of at least where client and server distinction, and then try and figure out what the problem is. And we're also introducing hunting by labels as well too. So often in an investigation you want to label groups of machines, say these machines are similar in some way, maybe they're all compromised by the same Trojan or something like that. Or this is a particular part of the network that's different from the rest. We want to label these machines. And then we're going to be able to do that in the UI and then also hunt. So look at all those machines as a group. And so this is the kind of seed I want to plant before I wrap up. So next time you're thinking, oh, where's that thing again? I can't remember where that thing lives. Go look at the Go artifact store. Hopefully it's in there. And we've got a lot of stuff in there already. So chances are it might already be covered. If it isn't covered, or if you're thinking, oh, I just figured this thing out and I need to write it down somewhere and I'm going to put it on my internal wiki, okay, do that. But also, have a look at the Go artifact store. If we don't have it, or if it's wrong, or whatever, send us a pull request. That would be great. So here's a bunch of links to kind of more information. As I said, the code.google site for Go has a bunch of stuff on it, and the slides and the white paper will go up there. And there's also a link to the recall project there too. I'm happy to take any questions now. Yeah.
Does GRR have a good way to track changes to a system over time, or events where suddenly these files changed on a particular machine?
Yeah. So the question is, does Go have a way to track changes on a machine over time? And yeah, this is definitely a key design goal for Go. And the way we wanted to do it was on the server, actually. So as we collect stuff, we keep this access of time for basically forever. So if we ever statted a file, then we keep that, and we just kind of keep writing new versions for each time we stat it in the future. So the idea is that we can, then go back in time. We don't have it's not like on the client it fires an event every time a file is modified or anything like that. It's more like from the server you have to tell GR to collect it. But once it is collected, then yeah, this access of time is a very important thing for GR. Maybe here.
What's required on the client side? You do an agent list?
So what's required on the client side? It's a kind of zero configuration install. So it's an executable on Windows. It's a DMG on OS X. It's a deb or an RPM on Linux. But you need some way to install it. So you need some sort of management capability or something to install it, at least the first time. The agent itself has its own update mechanism, so you can update it once it's installed. But just like any good Trojan or malware, we need a foothold to start with. So that foothold needs to come from whatever you use to manage your network.
What's the blocks you're reporting?
What's the blocks? So it's just asking what the hashing is like for the file system blocks. So for the file system blocks in particular, we want an exact hash. It's not a fuzzy hash. So we want to know exactly these bytes. We have those. In general, though, like when we're talking about hashes in GR, we usually use SHA-256, and when we export hashes, then we do like MD5, SHA-1, SHA-256. I think here next. Yeah.
Do you have a way to delete a file or across all machines you want to destroy it out? Is there a way to do it?
So do we have a way to delete a file? So basically, this was something deliberate that we didn't want to do that. That we didn't want to. We wanted GR to be, for the most part, basically read-only, so that we could say, this is a forensics tool. We're not going to modify the system. We want to maintain the forensic integrity of the system as much as we can. We've got this agent on there, and we're doing stuff with it, so it's not like kind of dead disk forensics integrity, but we didn't want a capability that would allow us to modify stuff. Having said that, there is a way that you can use a signing key to sign arbitrary Python and then have GR run that. So if there was something we wanted to do, then there's the capability there to do that. So you can kind of keep the signing key offline and then only sign, like the thing that you want to run, and the GR client will check the signature on whatever it's going to run. Up here, I think.
Is there a way to schedule periodic recurring collections?
Yeah. Is there a way to schedule periodic collections? Yeah, there's the concept of a cron job. So you can create as many cron jobs as you like.
So
Client-to-server communication, does it use compression? Yes. So we use protobufs. You may or may not be familiar with protobufs, but kind of Google lives and dies by protobufs, and they've been open source, so we use the open source implementation of protobufs. So we get compression from that. So yeah, everything is compressed on the wire as much as we can. And encrypted, yeah. We actually sent it over HTTP, but we used compressed and signed protocol buffers over HTTP. Yes?
Is there a way to compare the data that comes up after the cron job? So let's say I scanned it today, and then I rescanned it tomorrow, and I want to compare diff to scans.
Yeah, is there a way to compare the results that you get from two different cron job runs? So it's not an inbuilt way, because you'd basically for each, it depends what data you're collecting, like kind of what comparison you want to do, but you can definitely do that. So you can, collect it now, collect it later, and then you can use the data store to look at the two different versions you got. Yeah. Maybe I haven't looked at this side of the room enough. Over here.
Anchor clients are extremely ephemeral and they're auto-scaling. Does that produce any kind of issue? Can the server handle that?
So is there a problem with lots of clients coming and going? No, not really. So the whole architecture has basically been designed around lots and lots of clients polling in, and we run this at scale. So clients come and go all the time. I mean, we've got thousands and thousands of laptops that pop up and go away all the time. They move networks all over the place. This is a very common thing. So the clients poll in, and basically the architecture is that we try not to iterate over the clients as a whole. So that means that we can scale, we can have a big scale, that we can kind of send jobs individually to clients, but we kind of don't try to open them all at once, so we can kind of spread things out. The question is mainly laptops or infrastructure servers, both, actually. Yeah.
So from static analysis of the binaries, you guys publish
Right. Do we do any static analysis of binaries? We don't really do it inside GR, so in our deployment, we basically do that outside. So we ship the binaries out. Is it the last question? Am I out of time? Oh, okay.
For example, when we compare the output of the file system and sleuthkit for certain directories,
Yeah.
would the GRR job do the comparison, or would the GRR job just get the data?
So if you want to compare operating system and sleuthkit, so operating system view and raw disk view, so there's kind of not a nice way to do this in the GUI or anything like that, but you can certainly, like, as long as you collect both ways, so you have to tell GR to look at both of these things, and then once you've got the results, then you can look at them. Yeah, you could do it. Yeah. Anyone else? One more? Yeah.
How do you query the data store? Is it you run SQL against it, or?
How do you query the data store? So it depends on the data store. So you can run MySQL. That's one of the backends we have. So in open source we have MySQL and Mongo are the options. So using regular ways that you could directly query those. So you don't have to go through GR. You can operate on the database directly if you like. I think there was one more here. Yeah. So we have over 100,000 clients. So the question was scale. How many? Scaling the server. So yeah, you can. It's hard to describe kind of exactly what is the best strategy, because I think it's going to depend largely on your environment for what scaling the server looks like. But you can definitely split out different functions. So there's database, there's workers, there's front ends. You can kind of split those all out, and then it's a balancing act of how many processes per machine you run, and then how many machines you run, and kind of finding the right balance there, because kind of just the way that Python works. So it's all Python. Just the way that Python works, you might, and depends like whether you're CPU bound or you're waiting on the database. So all of this is kind of requires like a bit of tweaking to operate at scale yourself. Yeah. Yeah. Sorry, what was the question?
Not only for users, but what about servers?
Do we run GR as a service? No.
Run put agents on the servers.
Oh, on the servers, yeah. Yeah, so we run it on laptops, desktops, servers, a bunch of stuff, yep. Yeah.
Would the GRR database be the right place, the knowledge base the right place for IOCs? For example, special directory, wildfire, the rootkit on the Linux. Should I put something like that into that database, or rather?
So the question is the knowledge base or artifacts the right place for IOCs? And this is a question that we've been asking ourselves quite a bit as well too. So there's definitely people in the community who are excited about writing OpenIOC support for Go. I'm not sure how that's going to go. Maybe that will be great. I think some of the kind of challenges there that we've thought about are you often just can't ingest an IOC and then just run it automatically, right? You have to have some sort of concept of how much is this going to cost me across my fleet? Like, if it's a hash, I can't just go hash the entire disk of every machine on the fleet. It's too expensive. If the IOC's badly written, like, if it does a recursive directory listing that, touches tens of thousands of files on a single machine, then do that across hundreds of thousands of machines, then it's not good. So that's kind of one problem. Another problem is we're not kind of really excited about XML as a description language. So I mean, one thing we have been thinking about is perhaps we can do the data description with the artifact format, and then maybe we can do the logic engine separately. So maybe we could use Yara, for example. So we could like describe the data with the artifact format, and then we could use Yara to say if this thing or that thing, then do this kind of thing. This is all kind of ideas at the moment, but as I said, we do have some people interested in kind of writing OpenIOC support in the GR, so that may or may not happen. Yeah.
Is the GR server tierable? So can you set, if you've got enclaves, can you set up a server that communicates with the master server, so you can set jobs up the master server, they propagate down the client state moves back up?
Yeah, so is the GR server tierable? Can you have kind of like a region and then like a master for that region and kind of move data in and out? That's certainly not how we run it. So it's kind of hard to answer these questions. So, there's nothing, I guess there's not really anything stopping you doing that, but it's not designed in GR to operate that way. And a lot of this is because of just kind of like how the Google infrastructure works. So we take full advantage of, the great infrastructure that we have. So yeah, we don't really run it that way. We have front ends that basically all the machines in the world talk to, and then they talk to the database. Yeah, we don't try and kind of shard by region or anything like that. Cool. I think we ran out of questions. Oh no, right, one more. Yeah, performance concerns. So on the client, yeah, definitely we have hard limits and soft limits for memory. So when we're idle, we always check like how much memory we're using, and we'll kill ourselves if we're going over the soft limit. And then we also have a nanny that watches the GR process, and if it gets over a hard limit, then it will kill GR itself. And we also have CPU limits and network bandwidth limits that we kind of tried to build built-in safety into this so that there's defaults for all of this stuff, and you can change them if it's causing a problem with what you're trying to do. But generally, kind of you won't consume a ridiculous amount of resources if you just use the default limits that we have. All right, maybe that's it.